Hi, welcome to Coding Bootcamp's YouTube channel. Subscribe now and join our live stream session later. See you.
Welcome to this course on blockchain development with Ethereum, presented by Coding Bootcamps. Introduction to blockchain development with Ethereum. How to develop blockchain applications on Ethereum. A little bit about our instructor. Jim Sullivan has a Bachelor of Science in Electrical Engineering and a Master's of Science in Computer Science, and also holds an MBA. Jim is a Master IBM instructor, an O'Reilly Media instructor, and senior blockchain developer with DC Webmakers. As a software engineer with 20 years experience, Jim leads an expert team in blockchain development, DevOps, cloud, application development, and is a safe methodologist. Jim's an expert in blockchain platforms like Ethereum, Hyperledger, and Corda. Some prerequisites you may want to consider: introduction to blockchain technology, introduction to JavaScript, learn Node.js, Express.js, and MongoDB, which is a NoSQL database. Very interesting. Here is a list of the topics covered in this class: introduction to Ethereum and Ethereum basics, first and second generation blockchains, Ethereum cryptography, the Ethereum network and smart contracts, Ethereum smart contract development with Remix, the structure of a smart contract in Ethereum, smart contract functions in Ethereum, Ethereum client-side applications, testing Ethereum contracts, and also Ethereum use cases. By the time this class is over, we will have developed a smart contract. We're using a framework, a development framework called Truffle, to develop the front end or the web UI for the application. And also we are using a simulated Ethereum node that's presented by Ganache, and we're also going to use the Truffle framework for deployment and for testing. Some follow-up classes you may want to seriously consider: blockchain cybersecurity, learning Solidity Programming by examples, blockchain development with Corda, Hyperledger Fabric for developers, Hyperledger Fabric for administrators, and Hyperledger Sawtooth for system administrators. Thank you for taking this course, and please continue to follow us on social media. Next, we'll see you in the session. Welcome to this lesson on the Introduction to Blockchain Development with Ethereum, presented by Coding Bootcamps. This is Ethereum Basics. A little bit about our instructor. Jim Sullivan is a senior blockchain instructor and developer at DC Webmakers. As a software engineer with 18 years of experience, Jim leads an expert team of blockchain developers. Also is an expert in DevOps, cloud, application development, and the safe agile methodology. Jim is also an expert in blockchain platforms like Hyperledger, Ethereum, Corda, and also multi-chain and EOS. These are some recommended prerequisites. However, these are not required prerequisites. So Ethereum is a global, open source, fully distributed peer-to-peer computer network. And here is its website. So Ethereum can be thought of as an operating network. And that, if it sounds like operating system, well, there is an analogy there. Just like an operating system can run several applications, an operating network can also run many or numerous applications. On Ethereum, users can write applications called decentralized applications, or dApps, that will transact or take action on digital currency called Ether. And the full network will be able to always run that application. and it is immutable on the Ethereum network. And Ether is Ethereum's native token. Before getting to the Ethereum network, let's discuss blockchain. So I guess you could say blockchain is a data repository, if you know, and we're going to avoid the term database for right now. Although a database and the blockchain have elements in common in that they are repositories of data, we will look at blockchain as storing records of transactions. So the way that a blockchain actually stores the data is in the form of a ledger, a digital ledger. So it tracks ownership of assets and it tracks changes of ownership in those assets. So records are only added to a blockchain, just like with a ledger. So any removals or changes in the ownership status or fractions of it are entered as a negative change in ownership, and then there's also positive changes in ownership. Balances can always be calculated. So a blockchain is quite scalable. So it is very scalable, has a unique construction, and it has key properties of security and immutability. So it is because of particularly these two attributes that blockchain is ideal for exchanging assets between two or more users without the involvement of trusted third parties. So until blockchain transactions, with few exceptions, always involved a third party to act as a trusted intermediary. And that third party ensures that the transactors receive their assets and that everybody gets paid. Trusted third parties is a service, and that service costs. And the involvement of a trusted third party also involves time. So anytime we purchase something with a credit card, we may notice that there are pending transactions or the transactions have not been completed yet. We make a deposit and that transaction has not been validated or completed yet. So that's the time. That's that some trusted third party is behind the scenes updating ledgers. Blockchain has the ability to allow transactors to directly update the ledgers peer-to-peer, and that lowers the cost and the time of the transaction. The first blockchain assets were cryptocurrency. It's agreed upon that the first modern blockchain applications was Bitcoin. So Bitcoin runs on a blockchain. So yes, it is the Bitcoin application that runs on the blockchain infrastructure. So the two are not the same, although there's a common misperception that Bitcoin and blockchain are the same thing. It's a similar analogy in the way that Google and Yahoo are applications that run on the internet. Obviously, Google and Yahoo are not the internet, although sometimes it seems that way. The internet is Google's and Yahoo's runtime environment. On a blockchain network, users or transactors conduct traditional commerce and agree on prices for items that they are buying and selling. On, say, Bitcoin, users send and receive digital Bitcoins between one another. So transactions on the Bitcoin network are limited to the Bitcoin native token. In other words, Bitcoins change ownership on the Bitcoin ledger, and the changing balances are reflected in each user's Bitcoin wallet. And once the transactions are completed, they are permanent records on the Bitcoin blockchain. And as a result of the Bitcoin application's success, it's been innovated and there has been progress relative to blockchain. So we can consider Bitcoin's blockchain as a first-generation blockchain. Ethereum is a second-generation blockchain. Most experts define the first-generation blockchains as blockchains that only manage or only transact their own native token. So there's no distributed applications. There are no custom assets. Whereas second-generation blockchains not only manage their own native token, they can manage any type of asset, and they can also run applications called smart contracts. So the emergence second generation blockchains have caused us to think about the way assets can be traded. Ethereum and other second generation blockchains have made it possible to exchange any type of asset, as well as important information on the blockchain. So we can tokenize information. We can tokenize user attention. Here, we hear a lot now about voting. So we can exchange votes, information for votes. So, electors or the public can send their vote assets to candidates on a blockchain. That part is not hard. Most developers can have that part up and running in a few. The hard part is validating who indeed is doing the voting. Blockchains such as Ethereum make it possible to model assets on a blockchain. So just like with Java or C++, we can model real-world objects. We can do the same thing on the Ethereum network. So we can exchange assets. We can model an automobile. Its VIN, its color, its make, its model, its year. Assets generally come in two varieties, tangible and intangible. So a tangible asset is something physical that we can touch, hence the name. So things like precious metals, homes, buildings, computers, laptops, phones. Intangible assets are things like an IOU, or a patent, or a copyright, or a trademark, or even computer files. Both tangible and intangible assets can be transacted on a blockchain, and we can use Ethereum for that. An asset is an entity of value, so that's that is the definition. Accountants say that assets are entities that result in positive cash flows for the owner. Money, property, these are all examples of assets. Ethereum and other blockchains run on a distributed network. So the developers of Ethereum came over from Bitcoin. They were all Bitcoin developers, and they took that concept of the distributed network over to Ethereum. This form of the network ensures the blockchain is always up and running and is less vulnerable to attack. Here is a centralized network with the central focal point. All nodes on this network communicate, but they communicate through the central focal point. If anyone wanted to attack this network, they can attack the central focal point. That brings the whole network down. We see here a decentralized network has several central focal points. Every node here can communicate with another node. However, they must communicate through a central focal point, and then the central focal points communicate. So this is somewhat less vulnerable to attack, but it still has can still be vulnerable at the focal points. Distributed networks, especially with Ethereum, where all the nodes are peers, exactly equal, if any of these nodes would go offline, another node can step in and take its place. If one or more nodes came under attack, those nodes can temporarily be removed from the network. And as soon as new nodes come back on, the data, the most recent data can be copied to those nodes. So it is high resiliency and less vulnerable to attack. So in what we talked about here in this lesson is the Ethereum structure, the Ethereum basics, and the blockchain architecture. Here is an assessment. And here are some additional resources. For additional resources, please consult your learning materials. And for additional training, please consult your learning materials. The next session is first and second generation blockchains. Thank you. Welcome to this lesson on the introduction to blockchain development using Ethereum, presented by Coding Bootcamps. First and second generation blockchains. Just a recap of information about our instructor.
Thanks for watching. Feel free to add your questions as comments down below.
And a recap about some courses you may want to take as well. And our introduction to Ethereum. So, blockchain progress. So all blockchains can record monetary transactions. So blockchains, at their heart, blockchains are ledgers. The monetary transactions can be cryptocurrencies, or even in some cases fiat currencies such as a US dollar. Bitcoin only transfers ownership of Bitcoin. So the Bitcoin network only manages its native token. Second generation blockchains track not only their native token, but also any kind of asset. So it can be financial instruments or information assets or hard assets such as precious metals, gold, real estate. Blockchains can transact the recording of such items as deeds, marriage and death registrations, elections, medical records, supply chains, and many more. Blockchain is a powerful asset tracking system. Another key aspect of second generation blockchains is they take computing action on transactions. So you can actually write applications that run on second generation blockchains. An event-driven blockchain adds many possibilities to the use cases, and rules can be written for the blockchain to take action on transactions. If that sounds like executing the terms of an agreement or a contract, you would be right. So these rules are computer programs called smart contracts. Smart contracts are deployed to the blockchain and run when called by blockchain events and or blockchain transactions. So smart contracts are nothing more than a computer program that runs on a blockchain. In spite of their names, smart contracts are not really legal contracts. They can enforce a legal agreement and they can carry out the terms of a contract. However, they are, again, computer programs that execute on a blockchain and enforce business rules, complete certain tasks, take action on transactions. The blockchain is a record keeper for the business tasks being completed. Just as any other blockchain data, smart contracts are immutable on the blockchain, so they can never be changed once deployed. If we want to deploy a new version of the smart contract, we must deploy a new version, and then that contract would be the updated one that would always run. The previous version is all data on the blockchain is immutable. A smart contract is updated when applying a new version of the smart contract. So you get another address for the new smart contract. With some exceptions, a blockchain is a single running ledger on independent and separate nodes. Well, Hyperledger is a good example of a blockchain where there are multiple ledgers, but in Ethereum and Bitcoin, there is a single ledger. The fact that there are single or multiple ledgers does not indicate whether a blockchain is second generation or first generation. Operators of the individual nodes are called miners. It just turns out that with Ethereum, all nodes are peers. There's only one node type, one ledger in Ethereum. A ledger must be synchronized, therefore the nodes must agree. So there is this concept of a consensus algorithm in Ethereum. Pending transactions are continually arriving on the blockchain, and these transactions must be verified and added to the blockchains. So primarily, this is what miners do. Miners validate transactions. When pending transactions come in, they create what's called a proposed block. As the pending transactions are verified, the proposed block fills up, and it soon becomes time for the block to be added to the blockchain. There is a certain continuous time interval where the transactions on the blockchain fill up a block. The miners complete their additions to the proposed block and they run a consensus algorithm. The idea here is to keep the ledger completely synchronized. So if you and I and a few others were maintaining what was supposed to be a single document and we were updating it and adding to it and editing it, the contents on that document would drift. And the idea here is to resynchronize it on a regular interval. So once a miner wins a competition, which is currently proof of work, the block is added to the blockchain, and then that new block is relayed to all the other nodes, thereby synchronizing the blockchain. And once the synchronization is complete, the cycle begins again. There are several types of consensus algorithms. Proof of work is currently what Ethereum is using. However, Ethereum 2 is moving toward something called proof of stake. Proof of work involves running a computer program that looks to solve a complicated puzzle. It's actually searching for a nonce. Nonce is a random number. The nonce is identified, and it becomes part of once the nonce is identified, it becomes a part of a hash for the next block. The proof of work validates whether a miner is contributing time, effort, electricity to the blockchain network. And once miners add a new block, they're rewarded in that blockchain's native token, which in the case of Ethereum would be Ether. Proof of work is very expensive, consumes a lot of electricity, as it requires an immense amount of computing power. And again, there all are alternatives to proof of work. Ethereum, with Ethereum 2, is planning to move toward proof of stake. As a matter of fact, one of the Ethereum test networks is already using proof of stake. Some alternatives listed below, you can see here, to the proof of work consensus algorithm. Proof of burn, proof of capacity, proof of elapsed time, and there's many more. So blockchains support public transparency, and it is 100% validatable by the community and anybody watching the transactions. Since a blockchain is distributed, miners manage each node, and a certain level of security is bundled with support for the community and transparency. Blockchain provides a clear view of custody, chains of custody for assets, making it a perfect tool to secure and manage supply chains. Some of the other benefits are anonymity, cryptography, the transaction transparency of the blockchain enable a trustless environment. So it's done right in the open, and everybody can see the updated ledgers, who was paid and when they were paid. The emergence of smart contracts now enables blockchain applications. We've already discussed this. Smart contracts can perform important tasks on the blockchain. Some of the disadvantages to a blockchain are there is a new skill set that the community has to learn. Blockchains are slower than centralized database applications. They consume a lot of energy. Blockchain networks cannot process the amount of transactions per second as centralized applications. So for instance, Ethereum can do anywhere from 15 to maybe 25 transactions per second. If you compare that to the Visa network, which does about 70,000 transactions per second, there's quite a difference there. So is a blockchain required? Not always. So the benefits of the blockchain are unique to its architecture. However, your solution may benefit from a blockchain, maybe not. Quite often a central database solution can also provide the solution you need. So here are some of the benefits that a blockchain delivers. And if your application needs these, like public transparency, high failure tolerance, high degree of transaction demand, trustless environment, low transaction fees. If your application needs this, then a blockchain may be a solution for you. Ethereum, so this is what we discussed, Ethereum and second generation blockchains, blockchain consensus, smart contracts, how smart contracts run, and the Ethereum and blockchain advantages and disadvantages. Please complete the assessment. And for additional resources, please consult your training materials. And for more training, please also consult your training materials. In our next session, we'll talk about Ethereum and cryptography. Thank you. Welcome to this lesson, Introduction to Blockchain Development with Ethereum, presented by Coding Bootcamps. Ethereum and cryptography. Here is some information about our instructor and some recommended additional information or even prerequisite information. So what we learned so far, we learned about smart contracts and we learned about the Ethereum blockchain. So we know that ledgers are not new. Ledgers have been used for centuries to record asset ownerships. Cryptography is also not new. Cryptography is a technique of taking a message and using a mathematical code hiding the message from adversaries, so preventing it from being read, change it to a form that's unreadable. Only the message's intended party has the mathematical key to decode the message and return it to its readable form. Same strategy is used today to secure messages on computer networks, including government, healthcare, e-commerce, defense, the list goes on. Everybody who communicates on computer networks uses some form of cryptography. Today's cryptography techniques are much more complex than those of the past. We all use cryptography every day. Every day we conduct e-commerce or shop online. If you notice there's a URL that says HTTPS, that's the protocol that uses cryptography to secure the transactor's messages. And when a transaction completes, the transaction's details are written to the Ethereum blockchain. Just as described earlier, all transactions on the blockchain are permanent. And a blockchain uses a mathematical algorithm called a hash to ensure that records are immutable. Hashes are not necessarily part of cryptography. However, it is a mathematical function, and the hashes are often linked or presented around the same time cryptography is presented. And a hash, again, is a digest of data. So key pair encryption or asymmetric encryption is used to ensure that only the intended party can read a message. So each user has a key pair, a private and a public key. Each user's keys are mathematically related and they are generated together. All users know a user's public key. So the whole community knows a user's public key. That's the way we send information. We send information to the public key. It's no different than when we send information to your home. We have to know your home address. And again, all the community knows a user's public key. In hashing, all strings, no matter how long, can be entered into a mathematical algorithm that will output a unique string of a fixed character length. So names can be hashed, the entire text of Wikipedia can be hashed, the entire text of really any big book can be hashed to a string of a certain length. Hashing is very sensitive to changes. So even if one change in one small character will cause the hash value to change. On the blockchain, after a block is finalized, the data in the block is hashed to a unique string. That unique string is used as a header in the next block, therefore relating the two blocks together. The blocks are essentially chained together by these unique hashes. Again, if any data in any block and anywhere is changed, the hashes will change and the chain will be broken. So blockchain can be thought of as maybe change apparent, and then once that change is detected, it can be overwritten with a blockchain or a ledger or a block that has not been tampered with. So we will know if there is any tampering because we will see the change in the hash. Again, hashes are digests of data. Any data value can be stored into a fixed alphanumeric string, and there are many different types of hash algorithms. MD5, SHA-256. We can see here, this question here can be hashed into this 32 character.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
String. This way of saying a million can be hashed into this 32 character string. This 0 can be hashed into this 32 character string. And this paragraph here, which is part of the Gettysburg Address, can be hashed into this 32 character string. So how are the blocks chained together? So we could see here in this transaction 1, George and Bob are transacting. Bob is sending 100 Bitcoin to George. And we can see here Bob's account is debited 100 Bitcoin. George's account is credited 100 Bitcoin. Jay and Mark in transaction 2 are transacting. Jay is paying 10 Bitcoin to Mark, so Jay's account is debited by 10 Bitcoin. Mark's account is credited. So ultimately, this block will fill up and it'll be hashed. So this is a very simplified version of the hash. We don't want to get into long numbers. It can get a little confusing as far as presentations. But we could see here that same signature is used in the next block. And then when this block fills up, it will get its own unique signature and the blocks will all get chained together. So if there was any tampering with, say, this block right here, if George said, well, if somebody thought George deserves 500 Bitcoin, if we see something like this, the hash will change and it will no longer be chained to the next block. And this will become change apparent. And once this is detected, it can be overwritten with the correct data. So again, your public key is the key used by the public to encrypt messages for an intended party. So the public will use your public key to encrypt messages meant for you. Therefore, the community knows the public key of the user to which they want to send Ether. They have to know it. Only the intended user can decrypt the message, and that user uses the private key to decrypt the message. The user's private key is what's used to, I guess, open that mailbox and read the messages that are being sent. So everybody knows, again, our public mailing address, and then we unlock the mailbox to read the messages that were sent to us. So we could see here that Tom wants to send Kelly a message. So Tom will encrypt the message using Kelly's public key. So he'll send this message here, hi Kelly, encrypt it, and it'll become unreadable, and it'll get sent over. Kelly will receive the message, and she will use her private key to decrypt the message back to its readable form. As was previously stated, blockchains run on a distributed, decentralized network, and all computers or nodes are communicating with each other. Those computers, again, those hosts, are called nodes. And in Ethereum, all nodes are equal. They are all peers. There are no specialized nodes on Ethereum. That's not true on all blockchains. On some blockchains, we have specialty nodes. Nodes specialize. There is also one ledger, so every node contains a copy of the ledger. On some blockchains, nodes are the same, whereas on other blockchain nodes are specialized and perform specific tasks. So Hyperledger Fabric is an example where there are specialty nodes. The distributed network configuration is almost also like another layer of security. If tampering is detected on any node on the blockchain network, the affected node can be overwritten with data from the unaffected nodes. If any corruption would take place, the data can be overwritten with uncorrupted data. With distributed networks, all the nodes are working peer-to-peer. They're communicating peer-to-peer. The peer-to-peer nodes do not have a central focal point, and all the nodes host copies of the blockchain ledger. So on Ethereum, there's just one copy of the ledger, and all nodes have that copy of the ledger. Distributed networks have no central authority, and nobody is controlling the network. The redundant nature allows for fault tolerance. And if one or more peers go offline, they can be other nodes can go in and take their place. And when the offline node comes back online, they'll synchronize with the rest of the peers on the network. Distributed networks are also the least vulnerable to attack, because once an attack is detected, those nodes will just be brought off the network. And if they do come back on, they will be overwritten with the uncorrupted state of the ledger, the latest uncorrupted state of the ledger. And again, we looked at centralized networks, decentralized networks, and distributed networks. So here we talked about Ethereum encryption and ledgers, blockchain structure, cryptology, asynchronous encryption, Ethereum nodes, and distributed networks. Here is our assessment. And for additional resources, please consult your learning materials. And for additional training, please also consult your learning materials. And next, we're going to look at what makes Ethereum special. Thank you. Welcome to this lesson, Introduction to Blockchain Development with Ethereum, presented by Coding Bootcamps. What makes Ethereum special? We're going to take a look at the Ethereum network and smart contracts. Here is some information about our instructor. And here is some information about other courses you can take. So what we learned so far was we learned about hashing, cryptography. We had a little introduction to smart contracts, first and second generation blockchains. So now we're going to talk about some things you can do on the Ethereum network. So Ethereum is a public blockchain with all of the benefits described in a public blockchain. It was first conceived by Bitcoin developers who wanted to take the blockchain to the next step of running smart contracts to take action on asset transactions, and also to create applications. So Ethereum is considered to be an operating network, like previously discussed. Smart contracts are not legal contracts, but they are computer programs that can enforce the terms of an agreement, but they are the heart of blockchain applications. The Ethereum virtual machine is the smart contract runtime on the Ethereum network. The EVM is a bytecode compiler for smart contract programming languages. So what happens is you write your smart contract in one of the supported smart contract programming languages, and the Ethereum virtual machine compiles it into a bytecode. And then that bytecode is run on the Ethereum blockchain. So if it sounds like Java or .NET, it's the exact same idea. So developers write their contracts in Solidity, JavaScript, Viper. They are then compiled into a bytecode and then run on Ethereum. So the Ethereum network exists in a base of networks. So there's the live production network, and then there are several test networks currently right now. And you can also set up a private network for development as well. And you could install Ethereum software locally. If you go out and take a look, there are, again, several Ethereum networks. Most of them are test networks, making different tests such as consensus algorithms and testing different Ethereum additional feature testing. So we can see here, again, the live network. You can see the Robston and Rinkerby network, and then there's a private network, and there could be more than this. So a smart contract certainly has elements of traditional contracts. There's an agreement, and the contract is written in some kind of form. In our case, it could be it's written in a smart contract. There's a third party. It's either maybe a bank or a title company or a court, and then there's some type of execution on that contract. With a smart contract, it is peer-to-peer. So there's an agreement, a smart contract is written, assets are transacted, money can change hands, so that is the execution. And then the asset also changes hands. So here, if we take a look at this type of transaction, Sandy needs an outdoor light installed, and she hires Sam to install that light, and they agree to use a smart contract. In this case, we're going to use the escrow approach, which Ethereum can certainly do. Contracts can be written to take the escrow approach. So Sandy is going to upload her payment to escrow. And then as Sam completes certain conditions in the contract, he can get paid on those completed conditions. So a survey of the property needs to be done, and then a wire needs to be run. And after that wire run is complete and Sandy approves, Sam can get paid some cryptocurrency on Ethereum. And then once the light is installed, the remainder of the payment goes to Sam's account. So Ethereum smart contracts can be written in Solidity, Viper, JavaScript, many other high-level programming languages. No matter the programming language, they are all compiled to the bytecode through the EVM. And smart contracts are meant, again, to take events or actions on our transactions. And smart contracts manage Ether. They don't manage dollars or payments in that way. All payments are made using Ether. Solidity and its competitors operate in stages. So first, the logic is built in the form of source code, and then the logic is based on some kind of business rules or agreement. Then there is compiling by the EVM. At this stage, that program can self-manage and use private and public keys. And then as it's executing, that contract can update the Ethereum ledger. So the logic development in a smart contract or distributed application works in the same way that other application development is done. So logic is developed, there's some kind of compiling or building. There is public and private key management, no question about it, for your payments. And then when payments are made, the Ethereum ledger is updated. On the Bitcoin network, the native token is called a Bitcoin. And on Ethereum, we call the native token Ether. Ether is subdividable. So interestingly enough, the subdivisions are based on the smallest subdivision called a way. And the order of magnitude of one way and one Ether is 1 quintillion. So 10 to the 18th. That might be easier to say. And here are some other subdivisions. So we go from the way, which would be 10 to the first, all the way to the Ether, which is 10 to the 18th ways. So there's quite a bit of subdivision that can be done here. And this does help shield us from the volatility of cryptocurrency. And just like traditional transactions, there are some fees associated with the work that's done. And any work that's done for us on the blockchain, there is a fee for it, a very small fee. It's called gas. Gas is paid in Ether, so you will need some Ether to conduct your transactions. Just as traditional transactions have some kind of a Ethereum gas fees will differ depending upon the transactions, how they're run. Users should not view spending gas as any different from any kind of transaction fee. So Ethereum is not considered any more expensive. In fact, it's much, much less expensive. But gas fees are paid in Ether, and you will need to upload Ether to your Ethereum wallet to run on the Ethereum network. However, though, other blockchains like EOS and blockchains like that, it's the same thing. Priority is given to those that have more of that network's cryptocurrency. So with EOS, the more EOS coins you own, the higher priority your applications are to run on the EOS network. So you can take a look here and get an estimate of transaction costs. You can actually
Thanks for watching. Please like and share this video.
see it output as well in your Ethereum transaction. If you have a blockchain explorer, you can actually get this information. So the Ethereum, so we looked at Ethereum's design and mission. We talked about some smart contracts, how the Ethereum virtual machine works, the Ethereum networks, and the operations of the smart contracts, the Solidity and smart contract programming, payments, and Ethereum and subdividing. Before we move on, let's take a quick look here at, we can see here a smart contract, and this is code here. And this smart contract runs, well, first let's compile it. So I'm compiling it into a bytecode. And if we look here on the deployment, this initially is not going to run on the live Ethereum network. It's going to run on a simulated Ethereum network that they call the JavaScript VM network. But you can pick others, but we'll stick with the JavaScript VM network. And if we look here, we have all these public keys here that they give us. And notice that each of these public keys is given, I guess we can call it test ether. So we can conduct transactions. So you get this complete simulation of the Ethereum network. If we click deploy here, you can see that, oh, there's a little bit of gas that was paid. And if we take a look here, we can actually see the details of this transaction. You can see some way here that was part of the transaction. So let's view the assessment. And let's check our learning materials for some additional resources and additional training. So next, we'll do a deep dive into smart contracts. Thank you. Welcome to this lesson, Introduction to Blockchain Development, presented by Coding Bootcamps. So we're going to talk about smart contracts and do a smart contract lab. Again, here is a reprise of the information about our instructor. And again, some suggested prerequisite classes or additional classes. So what we learned so far, we learned about the smart contracts and the Ethereum virtual machine. We also learned about public blockchains, and we learned how smart contracts work, and we learned about networks. So now we're going to actually talk about developing a smart contract. So Remix is an integrated development environment for Ethereum. It's not the only development tool, but it's quite an impressive development tool. Remix is browser-based. Remix requires no installation, and it does use a simulated Ethereum node called the JavaScript environment. It has a rich text editor. It has the syntax highlighting. It click visual environment, point and click for compiling and deployment, and also visual debugging. So here's the address or the URL for Remix, and it does come with visual debugging, which is very, very good. Comes with our simulated Ethereum node and subdivided ether. And Remix has three major views: the editor view, the output view, and the explorer view. So if we take a look here, we can see what they call the modules or the icon view. And as you click on these, you will see the details of the module. And then there is the main view and also the terminal view. This is the file view or the file browser view. This is where we edit the contracts. You name them over here, you edit them over here. And then this is the smart contract running in the editor, and you're able to move through these modules such as compile and deployment. So to compile, we go over here to the compile module and click the compile button. And when we're ready to deploy, we move to the deployment module and click the deploy button. And when we're ready to run, we can go in here and actually run the functions, because after we deploy, we will get to actually execute our functions. So this is obviously a contract here. In this function set, it accepts a string, and if we click get, so we can see here the output when we click get. For debugging, we can set a breakpoint, and we can click the debug button, start debugging, and we can see these step buttons right here. So you could step over or step into, and you can see your values as you go through. So it's a visual debugger, and it is quite helpful. And we can also see results too. So if we have results output, we can see some results. We can also see outputs written to the Ethereum, the simulated Ethereum log. Here is the contract. So in your learning materials, we should have a contract. And so what we're going to do is paste it in. We're calling it my pay vendor contract. And the name of the file is mypayvendorcontract.sol. It's a Solidity file. And the name of the contract, if you look closely, is right here. So let's do a quick demo of it. Let's bring up our remix development environment. Here's our remix development environment. Here's our file module where we loaded the mypay vendor contract. So you see the name of the file and the contract name right here. So mypay vendor contract. And we won't go into too much detail, but what this actually does is it builds a vendor list. We can see here the structure of a vendor. The vendor gets an ID, a name, an Ethereum address. That's not a mailing address, and the amount owed to the vendor. Then we build up our vendors, so we can have 1, 2, 3, 4, as many as we need. And then what we are going to do is then input the address for the vendor, the Ethereum address for the vendor, and the amount that we need to pay, and it will then this function here will pay the vendor, and then we can send the payment. So for right now, don't worry too much about the syntax. So what we're going to do is click the compile button, or compile module, and then the compile button, and then we have a successful compile. Then we're going to click the deploy. So notice here we're in the JavaScript environment. And if we click here, we can see all of these simulated Ethereum accounts with test ether. You can see we've been using some of this. Don't worry if yours looks slightly different. We can see here the contract is mypay vendor contract, and here's the name here again. So we're going to, now that we're in the deploy module, we're going to click the deploy button, and we get a success on that. And we have to expand here next to this twisty here, and we are going to add vendor. So we're going to go in and add a vendor, and we're going to add an ID, a name, and an Ethereum address. So the name here will say, and it's got to be a string in this case, so we'll say Max's store. And we've got to get an address. So we need an address here from our simulated Ethereum node. We can't use our address. So we'll go to this drop down, we'll pick this address, and then we'll click this button here to copy to the, because that is, it's very long. And the amount owed, we'll say we owe Max 20 ETH for right now. And let's add let's add Max now. So we did that. We get a confirmation here that worked. That's good. Let's close this up. Now we want to issue our Ether. So have to go back here, make sure we issue it under the right address. So we want it to be our address, and let's say it's going to be 200 for right now. Okay, great, that worked. So here's where we have to keep track of our addresses. We have to make sure that my address and my vendor's address, we use them in the appropriate places, very role-based. Let's take a look at our balance. So if we go back and get our latest balance up here, again, copy the address, copy it in here, it should gives us the balance of 200. Great. Okay, that's what we expected. Our issuer, we can see here, here's our issuer address. Our issuer balance is still 200. Our vendor count is 1, but our vendors are 0 based. So we've got to put in vendor, we got to put in the ID of 0. And we can see we're getting back Max's store and his address, and then we owe Max 20. Okay, good. Okay, great. So now what I want to do is I want to make sure I pay Max. I'm going to clear this, and I'm going to click on this send, and we should be able to send 20 Ether over from my balance to Max's balance. Just so, let's get Max's address one more time, and let's put Max's address in here and get the balance. Oh, he is 0 now. Okay, great. And let's put our address back and make sure we have 200. Okay, great. All right. Let's clear the console. And the send button is like the pay button. So this is going to pay everybody. If we find send here, this is going to pay everybody that we owe. So it'll loop through all the vendors that we owe. So, but we only have one vendor, so it shouldn't be too long. So I'll click send, and that ran successfully. So if we come back in here, our address is still here. Let's click balance. Ooh, it went down by 20. Our balance went down by 20. Let's get Max's address. And hopefully Max's went up by 20. Oh, it did. Great. And the issuer balance also went down by 20. We'd expect that. Our vendor count is still going to be the same. And now we can see this other information is the same. So take a look at that. That'll give you some experience with compiling the contracts, deploying the contracts, running them, putting in the different addresses, because we have two actors here, two roles. We have me and Max and Max's store. So we're going to have two Ethereum addresses. So we want to make sure that we load up our wallets properly, our Ethereum address wallets properly. In this past case, it was 200. And then we paid 20 to Max's wallet. And here is what we looked at. We looked at smart contract development, simulated Ethereum accounts, the views and the panels, the compiler, the deployment, the debugging, running tests, editing smart contracts, deploying and running smart contracts on Remix, the Remix console, and the debugger. Please review the assessment. And for more resources, please consult your learning materials. And for more training, please consult your learning materials. Next, we'll talk about the structure of a smart contract. Thank you. Welcome to this lesson, Introduction to Blockchain Development with Ethereum, presented by Coding Bootcamps. Smart Contract Constructs. A review of information about our instructor, and a review about some classes you may want to look into. So what we have learned so far, we learned about smart contracts, executing smart contracts, developing them, the remix development environment. We learned about public and private blockchains, the
Thanks for watching. Feel free to add your questions as comments down below.
blockchain network. We learned about Ethereum and its structure. So now we're going to talk about smart contracts. So Ethereum smart contracts can be written in Solidity, Viper. We saw an example of Solidity in our previous lesson. However, no matter what the programming language, the Ethereum virtual machine deploys the smart contract to the Ethereum network. So smart contracts are meant to respond to events and transactions. And they also are how we build our distributed applications. So as we're going through development, one of the first items we want to take a look at it is the pragma. So pragma is not unique to Solidity. So the pragma is the keyword that invokes the compilers. So Solidity contractors will have different variations of pragma entries, and that version of the compiler must be available. There are different ways to indicate the compiler with the pragma. So we can see greater than or equal to, and these are compiler versions right here. A contract with a caret entry is it will not compile any version earlier than, in this case, 5.2. And so we can see it right here with the caret, and you can see other variations as well. Greater than or equal to, less than, so an in-between type of pragma. These are complicated. You might want to keep the pragma as simple as possible. So also comments. So code comments are important. Even some of the contracts we're going to take a look at in this lesson will have comments in there about what types of addresses or what roles we'll be running. You can do single line comments with the double slashes, or multi-line comments using the slash star and then star slash. And you can take a look at an example here. Exactly similar to Java, JavaScript, and C++. And then there are Boolean data types. So Boolean data types are a data type that is true or false. And we have here our negation data types here, or our negation operators. Our logical conjunctions, either the double ampersand or the and. Logical disjunction, either the double pipe, or equity with the double equals, or inequity with the bang equals. And you can see examples of it right here. We can see our bools. We can see our bools and they're initialized, and we can see some if statements. And then we also have our integers. So we have signed integers and unsigned integers. So this is the U, prefix U to int is unsigned. And you can see sizes for the integer as well. So we have 8, 256, unsigned integer, and then 256. So think about performance on the blockchain, and you will want to optimize your data. And then with our integers, we also have operators. So we have addition, subtraction, multiplication, division, modulo, and exponential. And these operators are the same as Java, C++, or JavaScript. And again, for the integers, they exhibit the exact same behavior. And you can see here also less than or equal to, equality, inequality, greater than or equal to, or greater than. And you can also strings. So strings must be inside quotes or double quotes. So you can see here 2 examples, hello and hello world. Strings cannot be directly compared in Solidity. So what Solidity does is compares the hash value of the strings. So if the hashes are the same, the strings are the same. If the hashes are equal, the strings are equal. So there's also an address data type in Ethereum, and there are 2 versions of the address data type. There is address and address payable. Address payable is the same as address, but also includes methods for transferring and sending. So again, address payable includes extra methods to transfer and send. Address payable supports address, and address payable supports sending Ether to another user's Ethereum wallet. And the address uses the same comparators as integer. So we can see here some examples of a wallet, and you can see here a wallet here. The address payable has the sender. Enums. So enums are custom data types. So enums, you can give them a specific name. They are zero indexed, and you can declare a value. So in this case, we have an enum called user options, or we have a user options enum. We see here, we declare that, and we see the options. So listen, connect, cancel. And then we declare a my option as user option, so which means it has the properties of user options. And then we can see here a constructor, and we want to initialize my option to the option cancel. And then for connect, we want to set it to connect, and so on. Another custom data type are structs. So structs are what we are going to use to model real-world objects. It's one of the tools. So we can see here we have a funder struct. So we need an address and an amount. So you can imagine what kind of data we want to build in here for funder. So again, this is one of the ways that we model real-world objects. Before we continue, let's take a quick look at the application we looked at yesterday. So we see in here that we have our structs. So this is the application we looked at yesterday. And we even have our addresses in here. So please take a look. We see another address here, issuer. So we have our various, a lot of the items that we're talking about now. So please go through this and take a look. Not everything is in here, but a lot of what we're looking at now is in here. You can see that if we used our enum in here to set certain conditions, payments can be made based on a certain condition. And we can see here that arrays are a data structure. So arrays are a way to have a variable with multiple values in different sections of memory. Arrays can be fixed or dynamic, and the size of the arrays can be declared at compile time. Values can be removed or added to the array based on methods push and pop. And the array length is used to add length to the array. So the length property is used. So adding values to the array, removing is a pop. And we can see here we have a strut right here of customer, and then we build an array of customer right here. You can see that we go through, we push different customers on here. So we actually loop through here and build an array of customers. Mappings are another data structure. So this data structure is similar to hash tables in that the values can be accessed using a key. So mappings are a key value type of data structure. So if we want to create a mapping called a customer, every customer gets a key or an ID and then other values associated with it. So to return the Mark Smith, we would request a key equal to 1. So it would be ID equal to 1. We can see here mappings set up here, vendors. So this mapping is called vendors. Another one is called balance. We have our struts here, our vendors, and then we build up we then build up our mappings here of various vendors. And we also can write certain data to the log. So with a blockchain, nothing is returned to the screen on the smart contract. You can interact with the screen, you can have a user interface, but with the smart contract, you don't. All of the events are written to the blockchain. So events are members of the contract in Ethereum. So an event, when an event is called, its arguments are stored in the transaction's log, and the log information can be seen when the transaction is mined. So the log is part of the record when the transaction is mined. So events are used with emit to manage writing to the log. So we can, and also we have loops. So loops have a construction exactly similar to Java, C++, JavaScript. There's a loop header, which consists in this case is a for loop, initialization and condition, and then the iterator, and then the loop will execute until the header condition. It will continue to loop while the header condition is true. And there's also a while loop. So a while loop also has a header condition. So we can see here while k is less than this array length, the expression will loop in the braces. It will loop through the expression in the braces as long as the condition in the header is true. And then there are do while loops, which are exactly similar to while loops, except you can guarantee that the expression will be executed at least one time. Handling errors. So currently right now, the error handling is limited to items such as require or checking ahead of time. Structures such as try-catch may be added in subsequent versions of Solidity, but currently right now there is no try-catch. So to prevent wasteful transactions from happening, we use require. So in this case, we could see require the amount has to be under 1,000. So we set that condition in order to receive a particular balance. If the require condition is not met, the transaction is rolled back. So we can see here a revert is called. And the revert function also triggers an error to display. And then that will roll back the transaction. So no ether is used, there's no wasted transactions. On a blockchain, once a transaction occurs, it's anonymous. So likelihood of reversing that transaction once it occurs is very remote. So we want to prevent transactions until we're absolutely sure that they should happen. So let's take a quick look again at our application. So we can see here, we see the mappings. And we can see here how we add to vendor. So the add vendor function, and what it does, it adds to the mappings. So we see here a vendor count, which is counted right here, the name of the vendor, the address, and the amount owed. So we can see here that's all included in the strut here. So the vendor ID is managed here by the counter. We can see the name, the address, and the amount owed, and that's the Ethereum address. And then we can see here a function where the requires are here. And we can see a for loop. And we can also see some emits in here. So we see our emits in here. So, and we can probably look up here, and see the event too. So what we want to do is we want to compile this. And then we want to deploy. And yesterday, in the previous lesson, we ran it. So take a look at running this. We'll go through very quickly. We'll say that this is Joe's store. And we need to give Joe an address. So let's get an address from here. And say the amount owed is 200. And issue, so we need a receiver address. Two different addresses. This is why comments are important. Let's say this is 500.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
And if we can do some testing here, test the balance, we can see we have 500 here. So as we go through here, we can click send, and that was successful. And now we can check our balance again. So it's down by 200 because we owe Joe 200. So if we put Joe's address in here, we can see that Joe has 200. Let's just get Joe's address. And I'm using, these names are very long, so copy paste obviously is a good tool to use. And let's try that. Oh, 200. Okay, great. And that was successful. And if we look through here, these logs, we may have to increase this. You can actually see the information emitted in here if you go through these logs. So, and you can see more information here. You can see an address, and but take a look at that as well. So please consult your lab materials for information on how to build and run this lab. Welcome to this lesson, Introduction to Blockchain Development, presented by Coding Bootcamps. Smart contract functions. And a little review about our instructor. And a review about other courses you may want to take, which will help you, give you additional knowledge beyond what we've discussed. So what we learned so far, we took a look at smart contracts, smart contract constructs. We took a look at Remix. We saw our Ethereum networks, and we saw that blockchain in general, it needs to be mined. Ethereum needs to be mined, and we learned about hashes and cryptology. So now we're going to be talking about functions in smart contracts. So functions in smart contracts, at least in Solidity, are very, very similar to functions in Java and C++. So if we can take a look here. Functions have visibility, so they can be public, private, internal, or external. It's an executable block. So a function is an executable block that performs some kind of an operation. Functions can take or return parameters, or they don't have to. They don't need to take anything or return anything. It's perhaps they just do something behind the scenes or pass a value back. So public functions are visible, and they can be called by other functions in the contract interface. So it's important to know to understand the visibility of your functions and also how they're structured within your contract. So we can see here we have a public function called get and another public function called set. The get, in this case, it returns two string values. In this case, we can see here it receives two values. So private functions are only visible within their own contract. So that means functions within their contract can call them. Private functions can be called by other functions within their own contract, but cannot be called by any functions in another contract. And functions declared as external can only be called from other contracts. So we can declare this in our current contract, but it can only be called from another contract. And we can see here that we have the function setInt, which is private. So again, it can only be called within this contract. But we see here setInt, which takes an integer. We can see it's being called down here in a different function. We can see set int with the j, which in this case is going to be an integer 256. And then this will be performed. These steps will be performed. So functions and data can be called from other contracts. So this is a lot like when you are instantiating instantiating an object in a function within Java. Very, very similar. We use the new command. So this way we declare one contract within another. Let's take a look. So we see here that there is this is a one Solidity file. In this case, it looks like how many? There are two contracts. So contract hold data, and there must be some kind of play on the double A. And then contract user base, so two contracts. Notice here, contract hold data, it is being called in contract user base, but they're using they're saying that HD is of type hold data, and we are instantiating a new hold data here, which calls in this case the implied constructor. There's obviously no constructor here. So it's running what's called an implied constructor. So now all of the functionality of hold data is available to user base through this HD contract right here, HD object. Solidity supports calling functions from other functions, and again, a function may return data, may not. It may take parameters, it may not. A function is called in the exact same way that it's called using Java, C++, or JavaScript. So again, here we have our function user count, which is down here. Notice how function user count is being called from, in this case, within the same contract. And it's internal in this case, so this public function add user the user count can only be called from within this contract. So as discussed earlier, functions can be called from another contract. The other contract must be instantiated again using new. So we already talked about this. So I can call hold data contract, but I've got to instantiate it using the new. And we saw an example of that a little bit earlier. Now I have HD available, and I'm able to call all of the data, all of the data types, and all of the functions that are part of hold data. If we went backwards a little bit, we would see that hold data has a public integer called data. And we can see that we're actually returning it right here. So this is a different contract, but we're actually able to call that public integer from the HD contract or hold data contract. Inheritance. So Solidity supports inheritance and polymorphism exactly the same way or similar to how Java and C++ support it. Inheritance between contracts is implemented using the is keyword. So inheritance is defined in the function header, and multiple inheritance is also supported. So if we take a look here, we can see that there is a contract here. In this case, well, again, there's two contracts. There's a contract called basic data, which looks like two public integers and has a function. And we'll write another function called user base, and then we'll use the is keyword in basic data. So now these two public integers are now available to user base, and this function is now available to user base. Also, we can also add to it. So user base is also not an exact duplicate of basic data. It also has new functions and new data that we are adding to it. So we can add other public integers and other items in here to then, that is the polymorphism. Now, deploying multiple contracts, we have to be careful. So once we compile this one Solidity file. The one Solidity file has multiple contracts. Next, we go to this dropdown and we select the contract we want to deploy. So let's take a quick look. So here I have my one Solidity file with several contracts in it. There's one contract, there's two contracts, and here's three contracts. I'm going to compile, and that compiles the whole file. That's fine. But when I deploy, I have a choice of three contracts that I can deploy. So if I start with user base and click deploy, I'm going to get output that looks like 1, 2, 3, 4, 5, 6. But now I can go up to basic data and I can click deploy. And I can see, okay, now I see 3 items here. So we've got to understand which contract we're deploying when we're talking about multiple contracts in a single Solidity file. So that's what we're talking about here, is just have to make sure that as we're interacting with this contract in Remix or in some other way, that we are working with the right contract. Return. So we could see here that if a function, if it's declared, if a return data is declared in the header, you could declare it in the header or in the statement. So we can see here that we are declaring here, this is supposed to be the header, the return statement, and then you don't need a separate return in the body, within the brackets or within the braces here, but it is optional either way. So no return is needed if we declare a return in the header. Pure functions, pure and view functions. So a pure function do not update or read the transactions block state values. So those state values must not be changed by any type of a function in Solidity. So because hashes are sensitive to changes, determinism is very key in blockchain. So a deterministic function is a function which will always return the same value every time. So pure functions do not access state values such as address balance. And we know our address balance can change. Pure functions do not access state variables such as block transactions or message. Pure functions only call other pure functions. So this is a function which, again, will return the same value every time. So we can see here that we have a pure function, and it looks like it's making a call to test P here. But notice test P is not a pure function. So, well, number one, we have a warning, and then we get an error here. And then we see if we change test P to a pure function, then we have no errors or warnings. So a view function. So just like pure functions, view functions do not modify the state. View functions do not write to state variables or emit events. View functions do not create other contracts or make ether calls. We can see here, like view functions, like pure functions, only work with other view or pure functions. And there are function modifiers. So function modifiers are a way to test for a certain condition before a function can run. Just like the name implies, it changes the way the function executes. A modifier is like a custom function type. Modifiers are called in the function's header. We'll see it up in the header. And modifiers can be inherited. So in this case, we see only admin. So we set up this modifier here. So you can see this, we declare a modifier saying that we require the message sender be equal to admin. And then when we set up this function, if this function will only run if the message sender is admin. And constructors. So constructors function much in the same way they do in Java, C++, and other object-oriented programming languages. They do the initialization for the contract as soon as it's deployed. They're the first functions to execute when the contract is deployed, or when we first call the contract. So once a contract runs.
Thanks for watching. Please like and share this video.
Once the whole contract is deployed to the blockchain, constructors are either private or public. And if we don't have a constructor, Solidity has a default or an implied constructor. So we can see here, this is how a constructor is declared. And again, this is for initialization. And you can also overload functions. So you can have several functions of the same name within a contract. How does Solidity know which function you're calling if they all have the same names? Well, it's the parameters. So the parameter pattern. So as if you have a function or an overloaded function that takes no parameters and then you call it with no parameters, the function with no parameters, that's the one that's going to be executed at runtime. Likewise, it will match the parameters in the header, such as string, integer. How that is called is how the function is selected. Exactly the same way it's done in Java or C++. So we can see here, this contract has two functions called add user. So we have add user that takes two strings, and then add user that takes nothing. So it looks like when we actually run it, Mike Sims, we have two strings right here. It will be this add user that is run when we click this button here. And time, so Ethereum time. So the Ethereum blockchain uses something called epoch time. So it's highly common. It's time that's maintained from a specific point in time called the epoch. And the epoch is the number in seconds since the epoch time. The epoch can be converted to any date and time, and we have function modifiers certainly can read Ethereum time. So it's good to have a function modifier if we say we wanted to start a initial coin offering and we needed it to only start after a certain day or on a certain day. We can put a function modifier there with a date time. And the current time can also be returned using block timestamps. That's another way to do it. And the current time can be compared to the epoch time in the future. So we could see here that maybe opening time for an initial coin offering is whatever this date is, and opening time, and only, as we can see here, will only start when we have only while open, and then we can see here only while open. So we can see here the epoch. So we obviously have to reach this time before this function can run. An address payable. So address payable is an Ethereum or Solidity data type that can receive Ether. Address payable is used when transaction results in payments made to another Ethereum address. So we can see here, if we take a look here, we see address payable right here. So before we do the summary, let's take a quick look at the lab. So we're going to work with a file called many contracts. Now it's very, very important that when you receive or when you see this file, you are going to see in the comments certain comments wrapped around parts of your functions. For instance, we comment out here where user data is, so we essentially take away the inheritance here. It's very important that you go in, you read all of these steps and remove the comments in the right way. So you're guided through this using step 1, step 2, and so just take a look at the steps. There's a step 3, a step 4, and a step 5. So follow those through very carefully. We want to paste this into Solidity. Obviously, we need to compile. And then again, we've got to pick which contract we want to deploy. So if we take a look at hold data here, so we know that hold data is instantiated in user base. So hold data and user base should have some items in common. Let's start with hold data. Deploy that. And we see that there are 2 items here, a public integer called data, and you can set the data. So let's type in 15 here and call it. And here this actually does something, right, when we set the data in here. And let's do this now. Let's deploy user base, because user base actually instantiates hold data. And we'll go down here, right below, and we can see here data, and here we call it the data, because we can see here the data, and set my data. So you can actually see here that we are calling we are using HD here, so they have some kind of commonality. So go through this lab. Just going to delete these now. Go through this lab, follow the steps, and consult your learning materials. So what we discussed here in this lesson was we learned about passing and returning data with a smart contract function, visibility of a function, private, public, calling and declaring functions, function inheritance, pure and view functions, function modifiers, constructors, overloading functions, and payable functions. Please complete the lab and complete this assessment. And please consult your learning materials for other information and additional training. And next we will do client-side applications. Thank you. Welcome to this lesson on blockchain development with Ethereum, presented by Coding Bootcamps. This is Ethereum client-side applications, and these are the building blocks of Ethereum distributed applications, or dApps. A little bit about our instructor. And we can see here some other courses that we may want to look into. And so far, we talked about Ethereum smart contract development using Remix. We looked at the Ethereum network. We looked at Ethereum mining and hashes and cryptography. And now we're moving on to client-side applications. So some of the tools we're going to need for client-side applications includes Node.js. So please go out and download Node.js. And we also need Ganache. So it is part of the Truffle suite. And what Ganache gives us is a private local Ethereum node. So it runs just like an Ethereum node. It has several accounts associated with it, and each account has 100 Ether. But you will need to create a workspace associated with your application. In this case, we have something called My List, but in yours, it can be called whatever is appropriate. So we want to develop using Ganache and Truffle because we want to develop locally first. Validate that the application is working, will solve the problem, and then we want to eventually deploy it to several Ethereum test networks before going to the Ethereum Live network. So again, we can see here one of the addresses, and we can see some Ether has been used. Very important, we need to know where Ganache is running. So it's running locally on port 8545. We also need to install MetaMask. So MetaMask is a browser extension that allows our browser to interact with the Ethereum network or an Ethereum node. And it's going to work with Ganache the exact same way it works with any Ethereum node. So we need to create a MetaMask account. So that involves a username and password that will log in. And we'll also need a wallet seed phrase because we need to also interact with our Ethereum wallet. And a seed phrase or a wallet seed is just simply a phrase that we keep secret, we keep hidden, so we can reconnect back to our Ethereum wallets. So we're validating here what version of Node.js we have. So we run here node -v to get the version. And we need to also install Truffle if we don't have it installed already. In this case, it was version 5.02. However, you can also install any version or even the latest. There is some information up at GitHub, but this may have also become dated, so please check back with your learning materials. To create a Truffle project, you run the command truffle init, and you can navigate through any Explorer, any window. It doesn't have to be Windows Explorer. It could be any visual folder explorer or system explorer, and you will see the Truffle project. So we need to create a Truffle directory first. Then we run truffle init. You can see it right here, and it will build up a framework for our Truffle project. We can take a quick look at this one. So we created this directory, and Truffle gave us this framework to start with. I have added one or two here since that time, but this is basically what you will have when we initialize a project with Truffle. One of the things we're going to do is we're going to compile a contract. So what I like to do is develop the contract for the most part within Remix. You can use another development environment. You don't have to use Remix. You can use Microsoft Code as well. There is a Solidity plugin for that. And then copy it into our Truffle project, and then we can also run Truffle compile from there. So if we take a quick look here, we can go into Solidity, and here is our smart contract. So we can literally just simply copy it in to our contracts folder. Here it is right here. And if we open this, we'll see our smart contract. So this is the copied in contract. And as we run our compiles, and we can also look for information, we can see here the various addresses that are part of the accounts that we're interacting with because we are connected to this node. And we can begin to run some command line commands on the deployed contract. So here we're able to test for a particular deployed contract. So we can see here the address for the contract. So by running the Truffle console, this is called the Truffle console, we can interact with the Truffle console really the same way that our distributed application interacts with it. And we can see here other Truffle console commands. So we can actually run functions from our smart contract. The add student function you can see here, we're adding a student and we'll get the transaction back. And we can also run information here and on the student that we just added and get IDs back and other items. And we can see here we can return information on student 1, student 2, and student 3. So we ran the student list here and it's returning information. So we're actually interacting with the smart contract right from the console. So this is querying output from our smart contract. And these examples show here how when we get to HTML and JavaScript, how they will actually interact as well. So this is communicating right with the contract that has been deployed to Ganache. This will be the same idea, same type of strategy that when we're working with a live Ethereum node. One other thing we're going to have to do is we're going to have to make sure that we connect our browser.
Thanks for watching. Feel free to add your questions as comments down below.
To Ganache. So when we start our browser, we're going to have to make sure that we are using localhost 8545 where Ganache is running. We've got to log in. And again, from this drop down, we have to make sure we're pointing to localhost 8545. And we will have to import an account from Ganache. So just so the MetaMask knows how to communicate. So importing the account will do that. You will also import other accounts for other live Ethereum, the live Ethereum network, and also for any test Ethereum. You can see some other test networks up here. One of the things we'll also have to do is get our private key. So the way we get our private key in Ganache is we click on this key icon for the account that we're working with. You see our private key here. We can actually copy that to the buffer, and we can paste that in here to MetaMask as we're importing the account. So we'll need to select private key, and we'll need to paste in our private key, and then finally click import. Now, Web3. Web3 is a tool for Ethereum. There are these Web3 docs. Web3 is, well, Ganache is part of it. Truffle is part of it. It has, we've all heard of Web, right? Web 2, Web 2.0. Now there's Web 3, which is really a set of tools for Ethereum, but it may be expanding to other blockchains. Web3.js is a set of API libraries which allows us to connect to the Ethereum node. So it uses the HTTP or IPC connections, and it enables us to interact with the Ethereum node. We can go into a lot more on that, but that's almost a class on its own. And you can install Web3 locally. You can see here the commands for that. One of the tools that comes with Node.js is a server called the Light server, and that's what we're going to use right now, is a Light server. So if it didn't install initially from your Node.js, here is the command to install Light server. And in our case, we're going to be running locally, so we will be running the command npm node package manager run dev. That will start our Light server in our development mode. And if we take a look at our Truffle contract, we'll need to create two files, app.js and index.html. These are the recommended names. You can call them other names. And if we take a look here, we can see in here how the Node.js, we've got to go in and do some editing, how we are connecting using the index.html and the Node.js to connect to our Ethereum node. You can see here how it's actually running commands very, very similar to the console, to the Truffle console. And Truffle actually gives us a lot of this. If we didn't have this, we'd have to do a lot of work on our own using the application binary interface. So this this might look like a lot, but this is the web3.js gives us a framework. I copied a lot of this already in, and I just simply edited what I needed to. Things like this, the Windows alert and other things. And the HTML here is actually a pointer back to other parts of the Web3.js, the JavaScript. So let's take a quick look before we do the summary. we go in here into source and we go into app.js, I downloaded again a lot of this, and so we can take a quick look at this. And what we are doing is part of where we are calling different parts of the smart contract actually comes in here and builds sections of a list which go back to which right here goes back to our HTML. So we can see here we have a ID student list or stud list, an ID called content. If we go back here to our app.js, we can see this stud list here or student list. So we can actually see the mapping here of how, and we can see completed list as well. We can actually see how our application is built. So the HTML and the JavaScript, the appearance or the rendering, there's some mapping involved. It's not too bad. And you can see here how, and again, this was a framework that I just copied in. A lot of this information was there, and I just simply went in and edited it. Now I've already run, if we go up here, I've already run Light Server, and so we see it running here, npm run dev, so this is up and running now. And if we go to the browser, we can actually see our list. So we can see we can see an Ethereum, or at least a wallet address here, and this one ends in 76. If we open up Ganache here, 76. So this is the address that I'm working with, and this is localhost at 8545. So MetaMask is set up here to point to localhost. If I go to this drop down here, we can see I'm pointing to the local host, and I have already imported the account. So we can see it's account for. So what I can do is click on the student list now, and if I wanted to mark Rob Thomas here as present, I can click that. Now what in this case what will happen is I will get prompted by MetaMask to confirm the transaction, and after the transaction is confirmed, we'll see now that Rob Thomas is marked as present. And we can also add somebody new. We can add Paul O'Brien, since that already came down. I don't think we have a Paul O'Brien doing no. You can click that, and MetaMask pops up and requests us to confirm. And as soon as we confirm, now that confirmed, there would normally be an exchange of Ether, but in this case, very little. This is all test Ether. And Paul O'Brien, I'll mark him as present. So that is an Ethereum application, and we are again running with our Ganache. That is our Ethereum node. And eventually we will, with the help of MetaMask and our deployments, we will go out and eventually run on these Ethereum test networks, and eventually the Ethereum main network, or the live network. So in summary, we looked at Ganache and Node.js, MetaMask. We discussed the Truffle suite. We were migrating and deploying a contract to Ethereum. We used Truffle console to call the contract. So we used Truffle console, and we started to interact with it to understand how our client-side application will interact with Ethereum. And we used the Truffle console as a dApp, and then we used Web3 and the other node packages to help us build a client-side application. Please review this assessment. And And for more resources, please consult your learning materials. Thank you. Welcome to this introduction to blockchain development with Ethereum, a presentation of coding bootcamps. This is testing Ethereum contracts. A little bit of information about the author and some other courses you may want to take. So far we have looked at Truffle and deploying contracts to Ganache and also to the Ethereum network. We have looked at actually running our Ethereum distributed application. We looked at Node.js and Node Package Manager. We have also looked at Remix and other smart contract development. We looked at cryptography, and we looked at the Ethereum network and mining, the types of Ethereum networks. So now we're going to talk about the testing frameworks. So Truffle gives us, well, Truffle and Remix both give us testing frameworks. So similar to they are unit testing frameworks. I guess we could say they're N-unit testing. It's very, very similar to J-unit testing or other types of unit testing. Windows also has unit testing. And we can see here that with unit testing, we can do test-driven development, we can do continuous integration, and we can also do regression testing. So this type of unit testing is very, very powerful. It is a great feature. Remix has a module, as a testing module, the double check here. And when you use Remix to create a test, it'll take your contract and it will create a new contract with the underscore test suffix. Then you're going to have to go in and do some modifications, though, to make sure that this new test actually calls your smart contract the right way. So when we go in and when we create our tests, we'll see the double check here, and you can click Run the tests, and the test will go ahead and run. Inside the double check, you can also generate a test file. So let's take a quick look here at Remix. And I've already run some tests because sometimes they take a little while. But you can see here how generate tests, we'll go in and it will give us, we'll use that framework. It'll use assert equals, and you can actually put in here some parameters. So when the test is called, it will validate that the same values are returned every time. The behavior is the same every time. So you can go back and do regression testing with this, because it is possible, even though you haven't worked on a certain function or a certain contract, sometimes it's possible to actually add a bug to an application without even realizing it. So these regression testing does a great job helping you discover any issues like that. So we can see here we have our tests, and what we did is I clicked Run the tests, and I just wanted to limit this slightly. And we can see here both tests ran and it was a pass. And sometimes this takes a little while to actually run this, so I'm not going to run it again, but I just ran these tests and we can see here the results. So the generating the test file, again, will create a framework for your testing. And Remix also has testing. So same general approach. You will create a test that actually call parts of your smart contract. So here we have a test, and you can see here we have the assert, just like with JUnit testing. You have the befores. So you can actually go through here. If you're familiar with JUnit testing, this is identical, and you can set this up here to actually call different sections of our smart contract to validate that they are still running and still returning the same information. And this is the contract that we're testing. And again, we can run this through Remix. Click the run tests and we'll get the output on the run tests. As we're setting up our, we can see here the assert OK to develop or to test whether a value is still true or false, equal.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
To a certain value, not equal to a certain value, so we can set these up to make sure that if any values are returned, they're returned successfully, or it's equal to some number that we'll know will always be true, not equal to some number we'll know will always be true, greater than a certain value or less than a certain value. And again, we looked at remix testing. Remix testing has the before each, before all, and the before functions supported. And we can see the before all, and we can see here as we are running the my contract one, and checking to make sure that the correct values are returned. And again, we can use we can also use Truffle for testing. So Truffle also has testing. It uses JavaScript. And the JavaScript tests are required before async, await, and assert for equality or inequality. And the it function block serves as a function where the test for a test name and lists of contract functions to evaluate a result. So the JavaScript testing uses the assert functions for evaluations of equality or inequality for pass or fail. So again, we can see here this JavaScript, and we can see the before, we can see the it functions here, and we can see the assert not equal to. So we're checking to say, oh, is our contract deployed successfully? As long as it does not have an address that returns like this, we know that the contract does have an address. And you can see here certain integers not equal to 0 and so on. And we're testing here for some string results. The way that we run the Truffle tests is we go in and we open up again either PowerShell, or we run our command prompt as administrator, and then we can run Truffle tests, and it will run the tests in our test folder. So let's take a quick look before we move on. We'll go into our test folder, and we can see our test here, our JavaScript tests. Open it up here, we can see our it functions, and we can see how we assert them to certain values. So these tests will run the same way every time. And I've already run them here. And I'm using command prompt here because the red shows up a little bit better, but you can easily do this through PowerShell. Again, if we run Truffle test here, that test will run. And I actually, so we can see it here, okay, 3 passing. So, and as long as you continue to do this, you can set up regression testing and automated regression testing for your smart contract. So here in this lesson, we learned how Ethereum supports testing, test automation, test-driven development, continuous integration, also automated strategies for automating testing. We looked at the remix testing module. We looked at building remix tests, running remix tests, Truffle tests with JavaScript, and building JavaScript tests with the require, before, await, async, assert, and the it functions, and then running the JavaScript test with Truffle. So take a look at this assessment. And And for more information, please consult your learning materials. And for additional training, please also consult your training materials. And in our next lesson, our next and final lesson, we will look at Ethereum use cases. Thank you. Welcome to this lesson, Introduction to Blockchain Development with Ethereum, presented by Coding Bootcamps. Ethereum use cases. And here is a little information about our instructor. And here is some other courses that you may want to take. So we have gone from learning the basic building blocks of the Ethereum operating network and the Ethereum blockchain all the way through developing smart contracts and Ethereum distributed applications, or Ethereum dApps. Please check your learning materials for downloading the code for all of the application and the smart contracts that we wrote. Your learning materials will have the latest GitHub repository for you to download the materials. So one thing we can use for Ethereum is one use case is fundraising. So the ERC20 is a standard for smart contracts, and the ERC20 tokens represent cryptocurrencies or other business assets. So you can use ERC20 to tokenize parts of your business or parts of your application. So it is, and you can actually sell those tokens in what is called an initial coin offering, or an ICO. So if you have an application that uses any kind of coins or points, you can use ERC20 to sell those ahead of time in an ICO, and you can raise money that way. You can also tokenize your business, so tokenize equity in your business. However, though, you may be issuing equity, you may be violating SEC rules. So it's very important to check with an expert on ICOs before going up and actually running an initial coin offering. Entertainment. So Ethereum is a great environment for managing information assets such as videos, music files, or images. Obviously, this kind of an asset can prove who owns it, because we talked about how behind the scenes, Ethereum also has its ledger. So we can prove who owns a particular video format and validate that they get paid. Also, supply chain. So supply chain applications can run on Ethereum. Often supply chains are made of disparate independent vendors with a common customer. The vendors don't want to share any information with each other. They only want to share it with the end customer. So things like lots, deliveries. The transparency of the blockchain makes traceability much easier. So if there's a problem in the supply chain, it can be tracked down. It can be tracked down right away. Also, personal data or user attention can also be tokenized. So the Brave web browser is a browser that uses a blockchain-based tokens. So the Ethereum ERC20 token, called the Basic Attention Token, or BAT, which you can buy on most exchanges like Coinbase or others, you can actually get paid in BAT as you allow for advertisers or if you interact with anybody using the Brave browser. So please check the video on brave.com. By default, Brave blocks all advertising, and then you will allow certain advertising, and you can receive payment in BAT for your attention on that advertising. Record keeping. So again, deeds, licenses are important assets. You can validate them with ownership, with signatures. So we saw private keys can be used as signatures, digital signatures, dates, date stamps, all of which are very important for such items as deeds, licenses, marriage certificates, death certificates, birth certificates, certificates of insurance, many more. So notary type of items can be managed or maintained on Ethereum. Internet of Things. So we know the Internet of Things is quite insecure. And so we have devices that are connecting to the internet. And these devices don't log in. However, using a blockchain application, we can store that login information so these devices can log in when needed in order to secure the Internet of Things. Loyalty programs are another type of asset that can be tokenized using Ethereum. They provide more flexibility, fraud reduction, reduce program costs, increase availability. Another advantage is if loyalty tokens are redeemable from other issuers, this can deliver data back to issuing merchants. So they will understand what their customers are doing and how they're using the tokens they issued. Healthcare, so obviously private healthcare information can be kept secure on a blockchain and only given or sent to physicians and healthcare providers, hospitals, and insurance companies. So we know that this is immutable and it is secure. So users can better manage their healthcare data using a blockchain like Ethereum. Smart cities. So smart city applications such as determining when lights should be turned green, when lights should be turned on, when green lights should be set to steady, can all be run through a blockchain in a much more secure type of environment. Also settling disputes, obviously validating ownerships, validating transactions with digital signatures. That type of transparency is all very desirable for settling disputes. So in summary, we talked about tokenizing use cases with Ethereum, ERC20 and fundraising use cases. So that was with the initial coin offering or ICO, entertainment and supply chain use cases, basic attention token or BAT in the Brave browser, record keeping or notary type of functions can also be managed on a blockchain. Internet of Things or IoT, loyalty programs, healthcare, and smart city and dispute resolutions. These are just some of the use cases. There'll be many more that we don't even know about today that we will see on Ethereum and other networks. Please take a look at this assessment. And again, for more information, more resources, please consult your learning materials. Also, there is a GitHub repository that will have all of the smart contracts and applications and dApps that we ran during this class. So please consult that repository or that GitHub repository. And here's more information on training, additional training. Thank you. Thank you for completing this class, Introduction to Blockchain Development with Ethereum. Again, a presentation by Coding Bootcamps. Again, we just completed Introduction to Blockchain Development with Ethereum, how to develop an Ethereum blockchain application. And here's a list of topics we just completed. Introduction to Ethereum and Ethereum basics. We looked at first and second generation blockchains. We looked at Ethereum cryptography, and we looked at the Ethereum network and smart contracts. And then we moved to Ethereum smart contract development on Remix and the structure of a smart contract on Ethereum and the functions in the Ethereum smart contract, building the client-side applications or the web front end to an Ethereum distributed application. We deployed our Ethereum distributed application and ran our Ethereum distributed application, or sometimes it's called a dApp. We tested and redeployed our Ethereum our Ethereum distributed application. And then we looked at Ethereum use cases. Congratulations on finishing this class and some other classes to consider. Introduction to Blockchain Cybersecurity, learning Solidity Program by Examples, learn blockchain development on Quarta, Hyperledger Fabric for developers, Hyperledger Fabric for administrators, and Hyperledger Sawtooth for administrators. Thank you again for taking this course, and please follow us on social media. See you in the next class.